You know, every single day, thousands of enormous ships are crisscrossing our oceans, carrying pretty much everything we own, from our phones to our food. But have you ever stopped to wonder what's actually moving these behemoths? Well, hidden deep inside their hulls are some of the biggest, most powerful engines ever built by humans. And today, we're going to dive deep into these mechanical hearts that literally drive global trade. Just look at this thing. We're talking about an engine the size of a 3-story building, with single pistons as tall as a person. Seriously, these are not just bigger versions of your car engine, they are a completely different animal, operating on a scale that is just, well, it's kind of hard to wrap your head around. All right, so here's the plan. We're going to break it all down. First, we'll take a quick trip back in time to see where they came from. Then, we'll get our hands dirty and figure out how they actually work. We'll peek inside at their massive parts, find out what they eat, and finally, learn what it takes to keep these absolute giants roaring across the ocean.
To really appreciate these modern marvels, you gotta go back. We need to travel to a time when steam ruled the waves and witness the moment when a new king arrived, the age of diesel.
And wow, what a takeover it was. I mean, the speed was just staggering. In 1914, diesel ships were basically a novelty. A mere decade later, their numbers had absolutely exploded. By 1940, they were dominating the seas. This wasn't just some small upgrade. This was a complete revolution in shipping. This image right here, it says it all. On the left, you've got one of the first internal combustion engines from way back in 1880. And on the right, its modern colossal descendant. We've gone from a machine that could fit in a small room to a machine that is a room. The basic idea is kind of the same, but the execution? It's on a whole other planet.
So, what's the secret sauce? How do they generate so much power? Well, it all comes down to this brilliantly simple, incredibly powerful process, the two-stroke cycle. Let's break down how it works.
See, the engine in your car is a 4-stroke. It takes 2 full rotations of the crankshaft to get 1 power stroke. But these giants, they do it in just 1 rotation. Every single time a piston goes down, it's a massive power stroke. That's double the power for every rotation, and that's exactly what you need to spin a propeller the size of a house.
It's this beautiful, brutal dance. First, the piston rockets up, squeezing air so tight it becomes insanely hot. Then, a fine mist of fuel is sprayed in and, boom, it ignites instantly. No spark plug needed. That explosion slams the piston back down with unbelievable force. But here's the clever part. As it gets near the bottom, exhaust ports open and a blast of fresh air rushes in, literally shoving the old exhaust gases out of the way. It's like exhaling and inhaling in a single powerful breath.
And that process of clearing out the old exhaust, it's called scavenging. And it is the absolute key to the two-stroke's power and efficiency. Instead of wasting a whole stroke just to push exhaust out, it uses pressurized air to blast it out. Think of it like using a leaf blower to clear a room instead of a broom. It's just way faster and way more effective.
Okay, so now that we know the process, let's meet the main players. We're going to go deep inside one of these engines to see the massive components that make this whole two-stroke dance happen.
This cross-section gives us an amazing look at the guts of the machine. You can really get a sense of the sheer scale here. I mean, everything you're seeing is built to withstand just incredible forces and to run non-stop 24/7 for weeks on end. So let's zoom in on some of the key parts.
First up, you have the piston, that massive plunger we were talking about. It's rocketing up and down inside the cylinder liner, which is basically a super tough sleeve designed to handle all that heat and pressure. The piston is attached to the connecting rod, a huge arm of steel that takes all that up and down violence and transfers it to the crankshaft at the very bottom. And that crankshaft, that's the final piece of the puzzle. It takes all that raw, linear power and turns it into the smooth, relentless rotation that moves a ship the size of a skyscraper through the water.
Now, an engine this big has let's say, a very particular diet. The fuel it burns and the oil that keeps it from seizing up are just as specialized as the engine itself. This is the lifeblood, and without it, this giant would grind to a halt in no time. So, these engines basically run on 2 main types of fuel. You've got marine diesel oil, or MDO, which is a cleaner, more refined option. But the real workhorse, the stuff that powers most of the global fleet, is heavy fuel oil, HFO. And this stuff, it's basically the thick, black, tar-like sludge that's left over at the bottom of the barrel after you refined crude oil. The big upside? It's super cheap. The downside? It's incredibly dirty and a real pain to work with. And if you want to see just how much of a pain it is, check out this viscosity chart. At room temperature, HFO is basically solid, like asphalt. You couldn't possibly pump it through a pipe. To even get it to flow like a liquid, ships have to heat it up to really high temperatures, just so it can be injected into the engine. Now, the lubrication is a cool two-part system. Down below, you've got circulation oil, which keeps the massive crankshaft and all its bearings running smoothly. But the real unsung hero here is the cylinder oil. This stuff is injected directly onto the cylinder walls, and it's designed to be burned away with the fuel. Its main job? To fight off and neutralize the nasty sulfuric acid that forms when you burn that cheap, high-sulfur heavy fuel oil. It's literally a sacrificial shield for the engine. Okay, so imagine running a machine non-stop for weeks at a time in the middle of a corrosive saltwater ocean, burning some of the dirtiest fuel on the planet. Yeah, that's a recipe for things to go wrong. So it's really no surprise that keeping these engines running is a monumental challenge all on its own.
The engineers on these ships are basically in a constant war. They're fighting a chemical assault from sulfuric acid trying to eat the engine from the inside out. They're fighting a physical battle against sludge and gunk from the HFO that tries to clog everything up. They're fighting corrosion from the very seawater they use to cool the engine. And all the while, they're fighting the relentless, brutal mechanical wear and tear from the engine's own incredible forces.
But here's the truly amazing part. Despite all of those challenges, these engines are unbelievably efficient. A modern two-stroke marine diesel can convert over 50% of the energy in its fuel directly into motion. For perspective, your car is lucky to hit 35%. This incredible efficiency makes them some of the most efficient heat engines ever built, and that helps keep the costs of everything you buy from overseas down.
And engineers are always pushing the envelope, trying to squeeze out every last drop of efficiency. Many modern ships now have waste heat recovery systems. These basically capture the super-hot exhaust gas and use it to boil water, create steam, and generate extra electricity for the ship. It's a genius way to get a little bit of extra power for free.
So what's next? Well, looking ahead, the future of these engines is really being shaped by two huge forces. One is that constant, relentless quest for even better fuel efficiency. And the other is the growing global pressure for cleaner, greener shipping with much stricter rules on emissions. The challenge now is to build engines that are not only powerful and efficient, but also much kinder to the planet.
For over 100 years, the giant diesel engine has powered global trade. It built the modern world we live in. But as we sail into a new century facing new challenges, you have to ask the question, what will be the next giant of the sea?